Our first speaker is Melanie Sanford, and obviously all of the speakers we have today are extremely well known, so we don't need to go through background and introduction. Melanie is a professor at the University of Michigan at Ann Arbor, and the title of her talk is New Strategies for the CH-Functionalization of Aliphatic Amines. All yours, Melanie.
Okay, great. Can you hear me?
Yes, we can hear you very nicely.
Okay, can I have the first slide? Actually, the second slide. Okay, so since I don't have much time, fortunately I talk fast, so I didn't have to shorten my talk that much. But in any case, I'm just going to sort of get right into it. My group for more than 10 years has been interested in the area of transition metal catalyzed CH bond functionalization. But one of the things that we particularly started to recognize in this field, especially over the past several years, is that there's a wide gap between the types of substrates that people typically use for these transformations and the types of substrates that are typically prevalent in many pharmaceuticals, drug candidates, and natural products, especially alkaloids. And so in particular, one of the things that we note, and is noted on this slide, is that aliphatic amines, while again very common in pharmaceuticals and drug candidates, as exemplified by some of the molecules at the bottom of this slide, remain rare substrates for transition metal catalyzed CH functionalization. And there are several reasons for this sort of dearth of amines in these types of reactions. If you go to the next slide. Amines, and this is really exemplified by the amine in the top left-hand corner of the slide, piperidine, tend to react either at the 1 or 2 position, so either at nitrogen or at the alpha position. And so shown on this slide are just some of the kind of typical reactions that will happen at nitrogen if you react an amine with a transition metal catalyst and an oxidant. So you can get binding to the metal, and this can irreversibly prevent your catalyst from turning over, or you can get N-oxidation of the amine to form an N-oxide. Next slide, please. In addition, chemistry often occurs at the 2 position, so the position that's directly alpha to the nitrogen. This position is highly activated, and so you can get alpha oxidation to form CH oxygenation products like the one in the box at the bottom right of the screen. In addition, iminium formation and dealkylation are sort of common reactions that will occur at this 2 position. And so although these types of reactions, particularly the ones at the bottom of the slide, can be quite useful, for example, in the generation of metabolites that are often formed that are what are formed using, for example, P450 enzymes, they are often not the products that So these can be useful reactions to generate metabolites. They can also be synthetically useful reactions. So if you go to the next slide, here are just a couple of really beautiful examples, including an example on the top of a CH functionalization of an alkaloid using rhodium carbene chemistry. And at the bottom, a ligand-directed CH functionalization of a piperidine core using a pendant directing group to direct the functionalization to occur at the alpha position. So alpha functionalization of amines is known and can be done quite effectively. What's much more challenging in this field is functionalization of amines, for example, piperidine, at positions other than the alpha position. Next slide, please. So what we targeted at the beginning of this project, and what I'm going to tell you about today is just one of the projects that we have in this general area of aliphatic amine CH functionalization. What we targeted was reactions in which we could take an amine, in particular, I'll focus today on piperidine, and use a transition metal catalyst in conjunction with an oxidant to selectively install a functional group at the 4 position. So this is the position that is most remote from the nitrogen. Next slide, please. So first, I want to briefly explain why we decided to focus on piperidines as an initial target for these types of reactions. So if you look at this recent JMed Chem review by Taylor, he says that piperidine is actually the 2nd most common ring in pharmaceuticals, second only to benzene. So this is an incredibly important structure, an incredibly important functional group. There were more than 12,000 piperidines examined clinically and preclinically between 1988 and 1998, just to give you a sense of the kind of number of molecules we're talking about. And as I exemplify at the bottom of this slide, 4 substituted piperidines are particularly common in bioactive molecules. And you can see a lot of sort of household names in the molecules at the bottom of this slide. Next slide, please. Okay, so how are we going to do this? Well, this is the approach that we decided to take. And the approach really leverages the sort of inherent nitrogen in the amine, in the piperidine, as a directing group for this chemistry. And so the idea, as you can see in the equilibrium at the top of the slide, is that we would imagine that a transition metal catalyst would bind really readily to this nitrogen. This can be problematic in certain other contexts, but we want to really take advantage of this binding to achieve the desired C4 functionalization. So as I show in the center of the slide, you can see that in the chair conformation, the metal bound at the axial position to the nitrogen is really in close proximity to H3. So this is the hydrogen at the 3 position. But CH activation can't occur at this position due to the fact that this would proceed to form a really highly strained metallocycle. It's a 4-membered metallocycle. So we didn't expect the reaction at the top of the slide to proceed. The other thing you'll notice is that when the metal binds to the nitrogen, H, at least in this chair conformation, H4 is quite far away from the metal. And so we really wouldn't expect the metal to be in close proximity to H4. Next slide, please. However, you could imagine that this is not a sort of conformationally rigid structure, and in fact is going to be undergoing conformational interconversions potentially between the chair and the boat conformation of the piperidine. And in the boat conformation, which is shown in the bottom center of the slide, you can imagine that H4 is now in quite a close proximity to the transition metal and might be able to undergo this transannular CH activation to generate the bicyclo-2,2,1 metallocycle shown on the bottom right of the slide. And so what we proposed, again, is that we could achieve selective C4 functionalization, C4H functionalization, through this minor boat conformer of the piperidine. So you might look at this initially and say that that looks about as implausible as the reaction at the top, right? Because this boat conformer is clearly not a very populated structure. But there were several pieces of evidence from the literature suggesting that this might actually be plausible. Next slide, please. So in 2009, Burkow had actually reported a stoichiometric CH activation of spartine. This was obtained by combining palladium acetate and spartine and allowing them to crystallize over a long period of time. And what he observed is that this CH activation actually occurred in this fashion exactly as I proposed on the previous slide. They observed transannular CH activation at the position that is effectively at the 4 position, remote to the nitrogen, to generate this same sort of bicyclic structure that I proposed on the previous slide. So obviously, spartine is a very special structure, but this at least, and this is a stoichiometric reaction, but this at least suggests the plausibility of what I proposed on the previous slide. In addition, if you go to the next slide, a very recent paper by a really beautiful paper by Matt Gaunt has demonstrated the feasibility of palladium-catalyzed amine-directed FP3CH functionalization. And so what Gaunt was able to show is that you could actually use amines as directing groups for sp3CH functionalization at sites that are remote to the nitrogen. What you'll notice in these cases, though, that's different from what we're trying to do, is that he always has the alpha position blocked. So the alpha position is always blocked with alkyl substituents, and this prevents alpha oxidation side reactions, which, as I mentioned a few slides ago, could potentially be problematic in what we're proposing to do. So again, what we'd really like to do is combine these two concepts and think about how we could conduct the transannular amine-directed CH functionalization, again, at these remote positions of piperidines. Next slide, please. Okay, so clearly there's a lot of challenges associated with this. As I mentioned earlier, there's going to be a pretty unfavorable equilibrium between the chair and the boat conformers, and we're going to need to deal with that. We also have the possibility for alpha oxidation. So we'd like to perform these reactions on substrates that don't contain substituents at the alpha position. And so we have to worry about alpha oxidation competing with the desired C4 oxidation. In addition, it's well known in palladium chemistry, and as you'll see, I'll talk about palladium chemistry, that secondary sp3CH activation is much more challenging in general than primary sp3CH activation. So we're going to need to contend with that issue as well. So to start to at least deal with some of these challenges, we decided to first look at a model substrate. Next slide, please. And the model substrate we chose was this 3-azabicyclo-3,1,0 hexane. I show it in its flat conformation on the far left, and in its three-dimensional conformation on the next sort of structure over. And I think you can see from the three-dimensional conformation that this molecule, by virtue of its structure, is actually pre-organized into a boat conformation. So that gives us hope that this structure should at least overcome the first challenge. In addition, it's really well known, particularly from Jin's beautiful work in the mid-2000s, that cyclopropane CH activation is generally easier than sort of regular secondary sp3-CH bond activation. And so for both of those reasons, we hope that this substrate would actually kind of serve as a good model for developing this chemistry. Next slide, please. So we evaluated a variety of different reaction conditions, and we were really pleased to see that we could, in fact, observe traces of this transannular CH arylation product from the reaction of this compound with palladium acetate and an aryl iodide. And this reaction appeared to be quite selective, although very small amounts of products were formed. So this was a really promising lead, but we did a lot of optimization, and we're really unable to optimize this initial reaction. And so if you go to the next slide, we hypothesized that what we might need to do here would be to actually tether a secondary directing group to the nitrogen in order to assist binding as well as potentially enhance the reactivity of these systems. And so the directing group we selected is shown sort of in the center of the slide. And it's really derived from a directing group that Jin has popularized in other contexts, this fluorinated amide. And what you can see from the structure in the center of the slide is that we've connected this fluorinated amide to the nitrogen of the piperidine, such that the piperidine nitrogen remains sp3 hybridized, so that it should be able to bind to the palladium in conjunction with the nitrogen of the sort of secondary directing group. Now, I want to point out something at this point that you might notice if you're familiar with Jin's beautiful chemistry, is that this doesn't look like it should work. If you go to the next slide, you'll see why. And that's because Jin has already shown in a variety of other contexts that, in fact, this directing group is an excellent, if you just replace the piperidine with an R, this group is an excellent directing group for sort of primary sp3 CH functionalization at methyl groups to form a 5-membered pallida cycle that then undergoes CH arylation. And so if you look at our structure at the top right, I think that at least initially you might expect that you would just get arylation at the methyl groups of the directing group. And so the only way that we can really preclude this from happening is if both of the nitrogens bind simultaneously. And so that's really going to need to be necessary in order for this reaction to proceed. Next slide, please. So we began to explore reaction conditions, and this just shows you one of the first reactions that we explored. This is the reaction of the substrate I showed you on the previous slide with palladium acetate, an aryl iodide, and silver pivolate at 120 degrees. And we were really pleased to find that, in fact, we do not observe any of the methyl CH arylation products. So suggesting, indeed, that these two nitrogens do bind simultaneously and that the methyl arylation is not a problematic byproduct. In addition, we see about 18% yield of the product that we desire, this transannular CH arylation product. And then we see the side product, and this is a side product derived from one of those undesirable side reactions that I alluded to, which is alpha oxidation. So you can imagine when you oxidize at the alpha position, generated an aminium ion, and that could be trapped by the sort of pendant directing group to generate this aminel product. And as you can see, this is the major product of this reaction. So we really wanted to understand where this alpha oxidation product came from so that we could prevent it from happening. And so if you go to the next slide, what you'll see is that a variety of control reactions showed us pretty clearly that silver pivolate was at least partially responsible or mainly responsible for this alpha oxidation reaction. So if we just treat the substrate with silver pivolate in the absence of palladium or aryl iodide, we get about 41% yield of the aminel. So clearly what we need to do here is replace the silver pivolate with some other pivolate source. And if you go to the next slide, I'll just show you what our thinking was in terms of how to do this. So this is just a very crude catalytic cycle for the reaction. And you can see that there's an initial CH activation step, transannular CH activation step, followed by the arylation reaction, and that leaves you with a palladium that has an iodide on it. And the role of the silver is proposed to be just replacing that iodide, abstracting that iodide, precipitating silver iodide, and regenerating the palladium carboxylate catalyst. So what we hypothesized is if we simply replace the silver carboxylate with a metal carboxylate that could abstract the iodide and generate an insoluble salt, but would not be oxidizing, that we should be able to limit the aminal formation. And if you go to the next slide, what you'll see is that we screened a variety of different pivolate salts and identified cesium pivolate ultimately as the best salt for this reaction. And so what you can see is that under these conditions, now it's simply replacing silver pivolate with cesium pivolate, we can now obtain nearly quantitative yield of the remote CH arylation product, the crystal structure of which is shown on the right-hand side, And again, the aminal is formed in less than 5% yield under these conditions. And just if you look at the crystal structure for a second, the only thing I want to point out here is that this reaction is clearly directed by the directing group and the amine. And as you can see, the aryl group is installed selectively on the sort of bottom face of this molecule. Next slide, please. Okay, so at this point, we had a directing group that was working. We had a reaction that was working really well. Obviously, this reaction isn't going to be so useful if you can't put the directing group on and you can't take it off. And so the next thing we really wanted to develop were conditions where we could install and remove the directing group in high yield. And so what I show you are just our first generation conditions in this regard. This reaction at the top of the slide just shows installation of the directing group. This proceeds in 80 to 90% yield with a variety of different amine substrates, so this works extremely well. And at the bottom of the slide, I show you our conditions for removing the directing group. These are our sort of first generation conditions that promote a reductive cleavage using samarium iodide. This reaction proceeds quantitatively. And as you can imagine, we're working on even more functional group tolerant conditions than samarium iodide. But at this point, the reductive cleavage with samarium iodide works quite well for this directing group removal. So really, we can do this series of reactions in quite high yield over 3 steps: installation of the directing group, CH arylation, and removal of the directing group. Next slide, please. Okay, so the next thing we wanted to do was look at the scope of aryl iodides that could be used under these reaction conditions, and you can see that this is actually quite broad. So aryl iodides with bearing both electron donating, electron withdrawing substituents work well, and you can see at the bottom of the slide in particular a variety of hetero-aryl as well as phenol and aldehyde containing aryl iodides work well. We can also use amino acid derivatives, and if we slightly modify the reaction conditions, we get minimal erosion of stereochemistry in the amino acids. So relatively complex substrates work quite well for this chemistry. Next slide, please. One of the things we wanted to do with this chemistry was to apply it to molecules that are of significant biological relevance, and this is just one example here. This is a molecule that was actually initially examined as a pain medication several years ago, I believe, by Merck. And it's recently emerged as a potential antidepressant. And you can see that it has the same sort of bicyclic scaffold that we've been functionalizing in the previous slides. And so we're able to very readily install the directing group onto this molecule. And using palladium acetate, cesium pivalate, and a variety of different aryl iodides, we can now access derivatives of this molecule quite rapidly, bearing a variety of different aryl groups. So demonstrating, I think, applicability to a biologically relevant scaffold. Next slide, please. Okay, so I've shown you the model system, I've shown you optimization of the model system, but clearly at the beginning of the talk, I promised you piperidine. And as you can imagine, and as we imagine, piperidine is a lot more challenging than this model system that's sort of pre-organized into the correct sort of geometry. Or correct conformer, I guess. The first thing that we did was actually collaborate with our young colleagues, Paul Zimmerman, to do some calculations and really try to understand how much harder it would be to functionalize piperidine. And so if you go to the next slide, what you'll see are some preliminary DFT calculations done in collaboration with Paul and Amanda Dewar, his graduate student. And these are just looking at the sort of transition states associated with the CMD, or concerted metallation deprotonation CH activation mechanism, for the bicyclo system at the top of the slide and for piperidine at the bottom of the slide. And what you can see from these initial calculations is that there's about a 6 kcal per mole difference in the transition state energy for the CH activation reaction. And if you look at the bottom left of the slide, what you can see is that 6 kcal per mole is essentially the chair-Bode isomerization of the piperidine. So as you might expect, once the molecule is in the right conformation, the CH activation proceeds with comparable activation energies for both substrates. Clearly we're going to need, this is a much harder reaction with piperidine than the model system as we had anticipated. And so if you go to the next slide, we started to evaluate a variety of different conditions with piperidine. What we found is that we got less than 10% yield when we conducted this reaction at 120 degrees. However, as you would expect for a reaction with a higher activation energy, as we increased the temperature and slightly modified the solvent, we were now able to get the desired product in about 54% yield. This yield isn't, is moderate. I'll talk about why that is in a second. But the bottom line is this reaction is highly selective for arylation at C4. So we don't see any other arylated products other than the one at this remote position. This is pretty exciting. I think that it would be pretty easy to argue that although this is a pretty cool reaction, it promotes this transannular CH arylation. If you wanted to make a 4-arylated piperidine, at least a very simple 4-arylated piperidine, this probably wouldn't be the way that you would do it. However, you can imagine that there's lots of other, for example, bicyclic piperidine scaffolds that would be much more difficult to arylate selectively at the 4 position. And so that's immediately what we wanted to look at were substrates that where it would be quite difficult synthetically to apply to install an aryl group at this remote position in any other way. And so if you go to the next slide, I just show you some examples of the kinds of substrates that work well for this chemistry. You can see a variety of different bicyclic scaffolds of various types now undergo this selective arylation, or in some cases diarylation, in quite good yields. And so again, the key thing that you want to note here is that the only arylated product that we see is arylation at the C4, or effectively the C4 position. We don't see any isomeric products in these transformations at all. So they're really highly selective. So again, we wanted to apply this to molecules that are really of relevance to medicinal chemists. And so one of the molecules that we identified right away after looking at some of these bicyclic scaffolds, if you go to the next slide, is Chantix. So this is a smoking cessation drug that has been developed by Pfizer. And you can see that it contains this piperidine core embedded in it. And so it's got this, so we were able to easily and in high yield append our directing group onto Chantix. And what you can see is that this reaction works quite well on this drug molecule. So using 10 mol% palladium and phenyl iodide, we can now get about 45% yield, highly selective. The only arylated product we observe is CH arylation at that effectively 4 position. I just show you the X-ray crystal structure of this product just to show you that this phenyl group is indeed, as you would expect based on the mechanism of this reaction, installed in the axial position. And I think it would be pretty hard to think about how to rapidly and selectively install a phenyl group at an axial position of this molecule in any other way. And what you can see at the bottom of the slide is that this works with a variety of other aryl iodides as well in reasonable yields, really providing, I think, a nice opportunity for doing SAR at this position if that's what you're interested in. Okay, so just to conclude then, because I want to stay on time, if you go to the next slide, you'll notice that some of the yields in these reactions are not quantitative. And we understand exactly why that is. So in fact, in these reactions, particularly with the piperidine substrates, we do indeed observe the alpha oxidation competing. And so even when we don't have silver in these reactions, we do see some alpha oxidation. We believe that that's catalyzed by palladium. And so we get a significant amount of this aminal product that's shown on the right. And that aminal, as you can imagine, is not able to undergo directed CH arylation. So this is sort of a dead-end reaction. And so what we really need to be able to do now is limit this competing alpha oxidation in order to be able to improve the yields of these reactions further. We have a lot of hypotheses about how to do this. And so we think that changing that pendant directing group is really going to be the way to go for that. And that's exactly what we're working on right now. But I just want to finish by leaving you with some preliminary results and opportunities, showing you, the kinds of things that we think we can do with this kind of chemistry. So just to go to the last slide, these are just some preliminary results that show other sort of things that are possible with this chemistry, especially pending sort of dealing with this competitive aminal formation. So of course, one class of substrates that are quite interesting are 3 and 2,3 substituted piperidines. These are very common in drug molecules. And so some of our preliminary results show that we can indeed functionalize these with reasonable diastereoselectivity selectivity. So in the case of simple 3-methylpiperidine, we're able to functionalize with about 7-to-1 diastereoselectivity selectivity for the trans isomer. We're also working on functionalizing other bioactive compounds. Cytosine is another example of this is in a natural product. It's also a smoking cessation compound, and we can now CH arylate this in reasonable yields. And even more excitingly, I just show you 2 examples at the bottom of the slide that show that we're not limited to just the simple piperidine core. So if you look at the molecule on the bottom left, you can see that we actually obtained diarylation. We got arylation on the sort of piperidine sort of portion of this molecule, as well as at the bottom of the molecule where there's actually a 7-membered ring. And so we believe that this will hopefully be a much broader reaction for other transannular CH arylations. I'm going to just show you at on the bottom right an example of a 5-5 ring structure. Again, this undergoes quite high yielding CH arylation very selectively at the CH bond that's highlighted. I guess that's all I wanted to talk about today. I want to just finish, if you go to the next slide, by thanking the coworkers that actually did this work. This work was done by 2 people, Pablo Cabrera, who's a graduate student in my group, and then Joe Tupchevsky, who was a postdoc in my group, really came up with this idea to begin with, and has just started an independent career at the University of Minnesota. So you can expect great things from him there. And then I just want to finish on the very last slide thanking the NIH, which funded all of this work. And I want to thank you for inviting me. I guess thank you for inviting me to this event. I hope that the estimates of the crowd are going to be, real estimates and not sort of Donald Trump type estimates of how big the crowd was here. But yeah, anyway, I want to thank you for inviting me. And again, I'm happy to answer any questions that anyone has. So thanks.
Well, thanks very much, Melanie. That's why we need the photographs to really prove the numbers. We've got some questions coming in for you, and so let me ask those for you. There's one from the TROS group asking, is any portion of the directing group recoverable following the samarium iodide cleavage?
Yeah, so that's a great question. So it turns out that in the case of the reductive cleavage with samarium iodide, you actually lose 2 of the fluorines from the directing group. So actually on the aromatic ring, you lose those 2 orthofluorines. So that's what we observe as the main byproduct of that reductive cleavage. What we're working on now is sort of milder cleavage, either reductive or otherwise, that will hopefully be able to allow you to recycle the directing group. But at this point, you do start seeing reduction of those aryl fluoride bonds under those conditions.
Okay, thank you. And just for everyone to be aware, if you have any questions, then please enter your questions at the chat room, and I will try to answer them in the most in the most reasonable way. So another question for you. This is from Nick. I can't quite catch the last name. The question is, did you see any issues with very bulky aryl iodides for the CH amination reaction on the model substrate? I saw the range of electronics, but what about naphthyl or anthracyl iodides?
I'm not sure that we've actually looked at very sterically bulky aryl iodides, to be honest. That's something that we should do. But I think that what I showed you was pretty much what we have looked at this point. So as you can see, this is all unpublished and preliminary. But yes, I would say that that's pretty much the scope of things that we've looked at. But that's certainly something that we will take a look at. Okay, great.
Have you tried to extend it to tropanes?
So again, one of the things that we're limited by is that so the substrates that I've shown you are the majority of the substrates that we've actually looked at. We have not spent a lot of time on that. That's certainly something that we'd be interested in doing. And I think just one of the things that we're limited by is access to interesting scaffolds. Some of these things, if you want to make it, it takes a lot of steps. And if you want to buy it, it costs, $2,000 for a small amount. So I think if there's people that have interesting substrates that they would like us to try, we would love to do it. So I guess I'd put a call out there. If you've got an amine that you'd like to, see if it works, we'd love to try it. Just send us some.
Okay, great. Okay, so thanks very much, Melanie. An excellent talk.